Okay. So in this example, we have a motor that drives a load with an inertia of J2. J2 is the inertia. Motor itself has an inertia of J1. Motor provides a torque of T, and the motor shaft rotates with theta 1, and the driving shaft rotates with theta 2. They are not the same. And in the gear, there is the gear ratio of N, which is N2 over N1, number of teeth divided, and that is equal to theta 1 dot over theta 2 dot, and that is equal to T2 over T1. Okay. The gear ratio, as you know. Okay. The shafts are massless and rigid. We want to find the following. Theta 2 of S divided by T of S. That is the transfer function that relates theta 2, the rotation of the shaft J, the second shaft, to the first, the torque generated by the motor. And the motor itself has a inertia. Basically, what we need to do is draw free body diagram for each inertia, then write the summation of the moments. Well, we say moments, J times alpha, J times theta double dot, that is, for each inertia, okay? Okay, so that's what we will be doing. For the first one, J1, for the motor, that is, this is our picture, looks like this. This is the gear. The motor generates a torque of, let's say, P of T. This rotates with theta 1. This is J1. Now, the gear has a certain torque on it, and it's in the opposite direction. Let's call it T1. This is okay. So the summation of the moments about this thing, M1 equals, we take the direction of theta 1 as positive, so it is T of T. And by the way, there is also I forgot that. BT1 times theta 1 dot. The viscous friction torque, BT1 times theta 1 dot minus T1. They both oppose the motion, both this one, BT1 theta 1 dot and T1, equals J1 theta 1 double dot. This is our first equation. For J2, we have the gear first. that is connected to, let's say, J2. Oh, well, this is T2 gear. This is the torque on gear 2. There is the opposing torque, which is T2. Dot. And J2, yes, that's here. So okay. Okay. So these are our two equations. But this is not all. We also have gear equations. That is the kinematic kind of equations. We have T2 is equal to MT1 is our third equation. And theta 1 dot equals and theta 2 dot. That's our fourth equation. Actually, we have four equations. And what do we have? Four equations with unknowns, or the variables are as follows. You have, well, theta 1 and its derivatives, theta 2 and its derivatives. T1, T2 are on, yes, T1 and T2. What do we want to eliminate? We want to eliminate theta 1, T1, T2. We want to eliminate three of them. Theta 1, T1, and T2, and we will be left with theta 2 and T. That is what we want. So we have four equations. So using those four equations, we can eliminate three variables. It's not too difficult to do that. But to do that, we need to Laplace transform our equations, or replace replace d by dt with s. Okay, if you do that, the equations we have will look like the following. So four equations, as you see. We just have to, we want to eliminate theta 1. So instead of theta 1, whatever we see, we put theta 2. For example, this theta 1 equation. So the first equation will look like J1S squared plus E T1S times theta 2, theta 1, sorry. Theta 1 is M theta 2 of S equals, we want to eliminate T1 also, T of S minus T1. T1 is T2 over N, and we will eliminate T2 as well. But T2 is this, the second equation. So let me write it this way, equals T of S minus T2, 1 over N. T2 is this, the second equation, J2S squared plus T2 S. Now, if you look at this equation, this one, this side, and this side, you only have theta 2 terms in it, and no theta 1 or T2. You only have theta 2 and T. So you can write it as follows. J1N squared plus J2 S squared. T1. Yes. And then we can write theta of S, so theta 2 of S over T of S as follows. If you divide everything by N squared, what you are going to get will be 1 over N divided by okay. This is the result. Okay. As you see, J2 and BT2 are divided with N squared. These are the equivalent inertia and equivalent damping of the system when these things with the gearing are carried to the location of the let's say generated torque, which is the motor. But the torque, the inertia of the motor and the damping of the motor are still there. So do we have any questions?
Hojam,
Yes.
can you explain how you changed the form from the second last step to the last step?
You mean the one before the last to the last?
Yes.
I divided everything by N squared. Okay. So both sides divided by N squared, and then I have divided everything to each other.
Thank you, Hojam.
Hocam,
Yes.
I think I miss a part when we are choosing the directions of the torques. So,
Okay. Okay, you mean this one. Now,
yes.
this motor generates a torque, let's say, in one direction, whatever direction it is. It is in the theta one direction, right?
Okay.
Um, it's in the
So,
theta one direction. Torque is in the gear torque will be resisting that, so it's in the opposing direction. Okay.
okay.
Yes. So
Okay,
gear
hocam.
torque is in the opposing direction.
So how we choose the direction of BT?
VT.
BT.
That is again that opposes the motion. That is in the opposite direction. So it is it's again against the rotation of theta one. Okay. So this
Okay.
is damping and it's friction, so it opposes motion, kind of. Okay. The same thing is true here. In the second one, now T2 is driving the shaft. This is theta 2 is in this direction, as you know. Theta 2 and T2 are in the same direction. BT theta 2 opposes the motion.
Okay.
This is not theta 2 double dot, by the way. This is just theta 2. Theta 2 dot, I'm sorry. There's only one dot here. Okay. So, that is a very basic introduction to mechanical systems. You know, I tried to show you how to do things, derive equations. You can derive equations for systems using the energy method also, which I have shown in the 301 class. But energy method is limited to one single mass systems, okay? So let me just write it as a energy method, which is E equals, let's say, kinetic energy plus potential energy of the system. And you take the derivative of the energy and equate it to zero, or the power dissipated, or let's say not to net power, let's say. This is possible. It can be done, but this is limited to single degree of freedom, let's say, DOF systems. But of course, you can generalize this, but that is kind of advanced topic, so I'm not going to go into that in this course. The general method is to use Newton's laws of motion, F equals ma, torque equals I alpha, for each mass and inertia. Okay. All right. So we will go to one more topic. Of course, I will continue with the mechanical systems, but let's talk about something else now. Well, the equations we are talking about in this system, we try to use linear equations, okay? Because linear systems are simple, and if a system is linear, very important property is that superposition is possible. And otherwise, superposition is not possible. If the system is not linear, it is not possible, okay? For example, if you have a system like this, you have an input, let's say input is U, output is, for some reason, we call it Y. When is it linear? It is linear. There is a static relationship, Y equals f of U, a function, okay? When is this function linear? Well, you can draw it like this, a function, you know, it might be anything like this. But what I have drawn here is not a linear function. The linear function is something like this. It has to go through the origin, and it has to be of a straight line. So this one, y equals, let's say, some k times x is linear. Anything else is nonlinear. This is nonlinear. And nonlinear equations are hard to solve. By the way, we are not talking about just linear equations, but we are talking about linear differential equations. For example, dy dt plus, let's say, ky equals u of t. This is also linear. Okay, because it contains only linear terms of y and its derivatives in it. And the definition of a linearity is basically is the following. If you have an input that is a combination of two different inputs with A and B coefficients, nothing, this is just the definition. But now it is linear if this is true. A fu1 plus B fu2. Okay. If this is true, then the system is linear. This means superposition, basically. Okay? So linear combination of inputs produces an output that is a linear combination of the outputs. Okay? For example, y equals ku is linear. We can say that this is k times au1. It looks trivial, but it is something important. A ku1 plus b ku2. So this obeys what we have said before above. So it is linear. Whereas, for example, y equals ku squared, let's say, is not linear because it's k au1 plus bu2 squared. Okay, this is not equal to k a squared u1 squared plus k b squared u2 squared, because there is the extra term of, you know, 2ab u1 u2 etc. Okay, so not linear. And also, y equals, for example, sine u, y equals e to the u, y equals, I don't know, what can we say? Even the following, a plus, well, let's not use a, but a constant plus ku, even this is not linear, okay? Because it doesn't obey the equation. This is, of course, with a coordinate transformation, you can make the last one linear, but it is, strictly speaking, it's not linear. Now, differentiation and integration are linear. So, systems, differential equations, again, the same property applies. For example, y dot plus, let's say, ky equals u is linear. But if you have y dot plus ky squared equals u, is not a linear one, non-linear. It's a non-linear equation because of this y squared term. Or you have, remember we had the pendulum equation, theta double dot over g over L sine theta is equal to, what was it? 1 over ml squared t of t. Because of this sine theta term, it is this pendulum. Not non-linear, non-linear. But remember that we tried to make it approximately linear by saying that theta is approximately equal to sine theta for small theta, so that we made it approximate linearization. We said that theta double dot plus g over L theta equals 1 over L squared is the linear version of it. Linear, but it is approximate. Okay. Well, so if your equation contains terms like, I don't know, sine theta, x squared, you know, theta squared or y squared, y times u squared, etc. All these terms make the differential equation nonlinear. And nonlinear equations are hard to solve. That is, they are hard to deal with, mainly because you don't have this tool of superposition. So we need something to work with. And what we do is, if you have a nonlinear equation, especially for the purposes of control systems, we try to linearize them, okay? If you have a linear system, you have superposition in your hand, Laplace transform, frequency response, and other possible tools. Whereas if you have a nonlinear system, none of these are valid. None of them are, well, you don't have these tools. You only have some advanced tools of mathematics, but even that doesn't get you very far. So basically, we try to deal with linear equations. So what we do is we try to linearize nonlinear equations about an equilibrium point. And this is important, equilibrium point, okay? We assume that the system does not change much around the equilibrium, so that about that equilibrium, the system's response remains more or less the same. What we are doing in effect is the following, actually. If you have a nonlinear equation of this kind, let's say something like this, okay? We try to pass a straight line through it about this origin point, let's say. This is the nonlinear equation, whereas this is the approximate linear equation, as you see. But is it valid? Well, yes, around this point, it is quite okay. But as you get farther from the equilibrium, it becomes, let's say this is U, this is Y, input and output. Essentially, what we are doing is try to pass a straight line through this curve, actually, nothing more than that. So what we do is the following. Let's say that you have a function again, it might go through the origin or it might not go through the origin, it doesn't matter. Let's say that you have an equilibrium point here. This is your equilibrium point. This is U, this is Y, this is Y equals F of U. You have an equilibrium point here, U0. The equilibrium doesn't have to be in the origin, obviously. This is Y0. Okay. You want to pass a straight line from here and find the slope of that, and that will give you the equation. So what we do is, about a point.
Hocam, could you please explain what do you mean by equilibrium point?
Okay. Basically, for example, let me give you a physical example. Let's say you have a mass, you have a spring. K is not the spring, it's a spring. Let me just write spring. But this spring has let's say, force of the spring is, it is not K, but rather K, it's not Kx, but let's say it's Kx cubed, okay, for some reason. So it is a stiffening spring. What does this mean? It means that the spring, let's say, of this system, looks like this. This is X, this is F spring, which is Kx cubed. Okay. What is the equilibrium of this mass spring system? There is gravity, let's say, okay? What would be how would the system, if you left to itself without any forcing, the equilibrium would be mg equals kx0 cubed, so that the equilibrium point x0 would be, for example, mg over k to the power 1 over 3, right? This is the equilibrium displacement, for example. This is what we are talking about here. Okay? So the equilibrium point is something like this. Okay? And this would be, for example, in this case, x0, and that would be a corresponding f0, for example. That would be a equilibrium, okay? So,
thank you so much, hocam.
Okay, let's continue this thing. Y equals f of u, as we know. Now we can expand this in Taylor series. F of u0 about the equilibrium plus del f del u at u0 equal u minus u0 plus 1 over 2 factorial del squared f del u squared evaluated at u0 minus u0 squared plus, it goes on like this. Doesn't matter because we are going to ignore the terms. Actually, we are going to ignore the terms about higher than this thing to linearize the system. So what we are left with, y equals approximately f of u0 plus del f del u at u0 u minus u0. Yes, approximately, this is true. Okay. So we can write this as y minus f of u0 equals del f del u at u0 u minus u0. And now we define the following. We define the variables as deviation variables. From the equilibrium, okay? For example, delta y, I define it to be y minus y0, and delta u will be u minus u0. Or you can say that y is equal to y plus delta, y0 plus delta y, for example, and so on. So these are small changes around the equilibrium. But y minus y0 is y minus f of u0, right? This is y0 actually. And this is u minus u0. And what we see here is, from here, this would be delta y is equal to the derivative term, which I will call the slope m times. This term is delta U, where M is equal to del F del U evaluated at U0. So the slope of the curve. So you have a linear relationship, delta Y equals M times delta U is the linear relationship. Which is approximately valid, let's say, around the equilibrium point U0, Y0. Okay? So you can use this in your differential equation if necessary. Okay. Let's take a break here.